So in this video, we're going to be doing one final example. So in this example, we have the scenario in which we have a disk, right? And the area of the disk, let me draw a better disk. It's not really good. Okay, so that's a little better. Okay, so this disk has an area that's represented by 4 pi r squared, and we know that it's a surface area equation, and we know for a fact that what's given, I mean this is part of the problem, that is that the radius increases with time in such a way that the area increases at a constant 1 centimeter squared per second. So what it's saying is that the radius is increasing with time, so we have a dr by dt as positive, right? That's greater than 0, and basically at the same time the area increases at a constant rate. So basically dA by dt is going to increase, and it's going to be a positive value, 1 centimeter squared per second, right? So this is a piece of information that I have. So the question asks me to calculate what dr by dt is. It wants me to find out what the rate of change of the radius is at a particular value of the radius. So when the radius is equal to 10 centimeters, I want to find the rate of change. So this is not going to be a very difficult problem, but we'll try to find it using a very simple method. So we've talked about this in the previous lecture, that if we have dy by dx over here, we can convert this to dy by dt times dt by dx, right? And we can use an intermediate variable that we can use during the differentiation to convert that to an equation that's something we're provided with, right? So in this case, what is that going to be? So in this case, basically on the left hand side, we can see that we have the term area over here, right? So that kind of represents y and r represents x. So dA by dr is something I can determine over here, and dA by dr has to be equal to dA by dt, right? And that's the intermediate variable here. Can you guess what comes after that? Well, I think you can. It's basically dt by dr, because if the d's cancel out over here, we're going to get dA by dr. So this is the equation that we're going to use in this problem. So can we evaluate dA by dr? Of course we can. We have an equation in terms of A over here and R, right? So, and we have dA over dt as well. dt by dr is something we need to find. So let's just do that. A equals 4 pi r squared, right? So if we differentiate this, we get dA by dr, and that equals 8 pi r. Why does it equal 8 pi r? Because that's a constant. I don't care about that. How would you differentiate x squared? Basically, you just get 2x, right? So A equals 8 pi r using this logic. So all we can do is substitute this over here. So we get 8 pi r over here, right? And that is equal to dA by dt. We know dA by dt is positive 1 centimeter squared per second, right? We don't need to concern ourselves with the values right now. And dt by dr is simply 1 divided by dr by dt, right? If you think about it. And what we can do is we can take this to the other side, right? So we're going to get dr by dt on this side, and we can take this to the other side. So kind of like cross multiplication is what people refer this to. Okay, 8 pi r. So what's the problem over here? Well, we have something in terms of r, but we've been provided in the question that we want to find dr by dt when the value of r equals 10. So all we're going to do now is plug in the value of r, which is basically r equals 10. That's going to be 1 divided by 8 times pi times 10, and that's going to give us 1 divided by 80 pi. So basically what this question has done is it's given you an answer in terms of the radius. So what it's saying is that when the radius is r equals 10 centimeters, the rate of change of area is equal to 1 centimeter squared per second. The area is increasing by this amount every unit of time, because that's what it says over here, right? And at the same time, subsequently, basically, and or in better words, simultaneously, dr by dt is 1 divided by 80 pi centimeters per second, and the radius is increasing by that amount in the same amount of time. So and if you guys notice that this does not necessarily apply to just the value of r equals 10, any value of r could be plugged over here, and the resultant change with respect to time for the radius could be determined at that particular value of the radius. So that's the underlying concept over here. You could be given an example like this. Definitely, it's something that you guys should get on board with at this point, that applications is a very important part of differentiation, right? And if you need to get into that, always remember this equation. Always try to remember what they're asking for, and try to use the chain rule by using this equation. And if you use this equation, you convert this into 3 specific parts. One of these parts is going to be unknown, and the others are going to be provided to you in one form or another, right? And you'll be like using this to evaluate the correct answer, whatever they ask for. They could also ask for dA by dt, by the way. So that's pretty much it for this video. In the next video, we're going to be starting with linear approximation. So hope to see you guys there.